Hey there, everyone. My name is Ryan Schul. Welcome to my channel here. It's all about analytics and making predictions into the future, some data science, machine learning, deep learning, artificial intelligence, and things related to this. So in the narrative today, I want to talk about bridge deterioration prediction. Okay, so in most of my videos, I'm trying to predict something. In this case, it is the infrastructure all around America. This is a hot topic these days that is crumbling and disintegrating and basically deteriorating right underneath our own feet. So you can pretty much predict anything if you have the independent variables and the target variable. That's what you're trying to predict. So if you have that and the data is good and clean, pretty decent shape, you're not missing a lot of values or variables. It's pretty much intact and structured fairly well. You can make predictions on these things, right? Really, the sky's the limit. It's almost anything you can imagine. You can predict it. I read recently that Uber actually tries to predict which drivers they can take advantage of. This is kind of crazy, right? And the drivers that are the most desperate for money and most desperate to engage with work, they will target those drivers with less and less money, right? They pay them less and they'll still charge a high rate, and Uber keeps the margin in between, and they can predict the drivers that are likely to accept this lowball offer. It's pretty crazy and kind of very unscrupulous, I think, but you can even predict that if you want. Okay, so really, you can predict anything. So today we're not going to predict sketchy Uber business practices, but rather we're going to take a look at the infrastructure around America, specifically bridges. I have some data here that we can start to analyze. I have a bridge ID, so we have to identify the bridge some way. An identifier, some type of numeric would be preferred, but if it's not, it could be a name. As long as it's unique, it's totally fine. The age of the bridge in terms of years, the last inspection, how many years ago, traffic over the bridge, truck percent, the span length of the bridge, number of spans of the bridge, right? One versus many, seismic zone, and climate corrosion index. Okay, so there's a few different materials that the bridge can be created out of. It can be concrete, steel, or some type of composite material, which is a mix of a couple different things, right? Probably concrete and steel and maybe rebar, things like this, right? So material, is this concrete, is this steel? And we're going to try to make a prediction about the condition of the bridge now, and then the future state of the bridge, and how the bridge is likely to deteriorate over time, and maybe even, dare I say it, actually collapse, right? So, but that's what we're trying to predict and try to prevent too. So let me go ahead and run the cell here. I have all the code. As always, I'll share all this code with you guys, right? When I post a video, I'll post the code so you have everything that you need. You can take it, drop it right into your Jupyter notebook and run it as is, okay? So pretty easy there. So we want to look at, so here's the data frame, right? We have 13 different columns, 2,000 different rows. So you can see these are the items I just mentioned, right? So we have things like normal traffic, normal age, wear and tear in the bridge, things like this, right? Additional traffic, the bridge's age in terms of years, and last inspection in terms of like how long ago that was, okay? So we're going to assign a risk score based on things like the condition after 5 years, the any potential major defects after 5 years, normal traffic, is there normal or abnormal traffic? Is there higher traffic? Does it be more wear and tear in the bridge? And normal last inspection, okay? So things like this. Let me hit the Control Enter to refresh the cell. You can see the code working in real time right here. Well, it was working. Let's see, condition 5-year predict. Let me see, was I missing something here? Sometimes I go through and hack these things up and then I end up missing something. I think that's okay. Okay, let me take a look. Let me pause this thing 1 second. Okay, hang on. All right. So I found it in my notes. I was missing a couple columns. Trying to do operations on columns that don't exist is a recipe for disaster, guys. Okay, so make sure you have all the columns you need. I just popped them in, so you are good to go. Again, I'll share this code with you, so you have everything you need. Just copy, paste it, drop in these blocks of code into your Jupyter notebook, and you are good to go. So just to recap, right, we have the condition now. These are all based on metrics that we can analyze pretty easily, right? The age of the bridge, any kind of additional traffic, normal traffic, climate corrosion index, right? If you're in a cold climate or climate with a lot of moisture, humidity, a lot of heat, those could have impacts on the integrity of the structure, right? That can cause the structure to become impaired in a shorter period of time, things like this, right? So we're looking at normal traffic, normal age, additional traffic, age cumulative over the course of time, the age of the year, years of the bridge divided by the maximum. So we're trying to take this and basically normalize this metric right here. Anytime you divide by a max or maximize a min, you're trying to normalize the feature or the field that you're analyzing here, right? So climate corrosion index, truck percent. So trucks are heavier than cars. More trucks going over the bridge results in more wear and tear on the structure, right? So condition after 5 years, condition now, normal traffic, and normal last inspection date. So these are all important, right? It sounds pretty important, and it is very, very, very important, right? So we have to stay on top of these things. We have to understand what's going on and keep up to date with these things, right? The condition of the bridge can change very quickly. Time passes, whether you are ready for it or not. And you see it in the news all the time. This bridge is collapsing somewhere in the Midwest. This bridge collapsed in the Northeast. There's one, who knows where, in the Mid-Atlantic region and the West Coast, right? Just turn on the news and you'll see this all over the place, right? So sometimes it's neglect. Sometimes people just aren't really paying attention, and who knows what goes on. I don't know, but I think it is important to stay on top of these things, right? It's pretty easy. If you have the data, it's pretty easy to do these types of analysis, right? So let's step through, let's keep going with this. And again, like I alluded to before, you can predict anything you can imagine. This is wear and tear on bridges deteriorating and coming to the brink of collapse, right? But this doesn't have to be this way. If there's like normal inspections and you stay on top of these things, we can calculate the risk score. I'm going to show you how to do this very soon here. Calculate the risk score, and these are going to be the high priority, right? Number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The top 10 bridges in the United States right now that need to be inspected or need to be upgraded and repaired, right? You can determine that very easy if you have the data. If you don't have the data, then good luck, right? It's just a crapshoot. Nobody knows what's going on. If you have the data, it's actually pretty easy to do this. And other similar types of things too, right? This is just bridges that we're talking about. Any type of infrastructure, whether it's like a hydroelectric dam, whether it's a mass transit artery system or something like that, a subway, right? I live in New York City. The subway is decrepit. It's falling apart, day by day. If you keep track of these things and collect data, like accurate data about the facility or about the infrastructure, you can understand the current state and understand like when do you need to start doing these repairs. You want to be proactive and preempt some kind of catastrophe or disaster, right? So moving on here, so we're assigning some weights to age and years, climate corrosion index, and truck percentage. So again, the number of trucks going over the bridge, probably more weight, more stress on the structure, right? And that's going to contribute to an accelerated deterioration phase, right? So we are going to assign weights to these types of things and try to understand as we give it more weight or a little bit less weight, what kind of impact does that have too, okay? So let's move on here. Let me save it and refresh this. It's disappearing down here. We got a blank screen, so let me refresh this thing. Hang on a second here. All right, this is looking good right now. So we have all of our features in our data frame. As I discussed before, most of these are numeric. If not, most are numeric. We have one labeled feature over here. So anything that's numeric is number. Anything that's not numeric is a label, right? So with material, we can convert this to some type of numeric representation of some type of numeric representation of material. So concrete can be 1, steel can be 2, and what was the other one? The MEX or something, composite can be 3, right? But we can't feed concrete, steel, and composite into a machine learning algorithm. It has no idea what this is whatsoever, right? So once we convert that to numerics, we can go ahead and make our predictions. And this is going to be the predicted target that we are setting right here. So condition 5 years true. Okay, so that's what we're trying to predict. Is the condition 5 years from now true? Is it, is it good condition or poor condition? And based on that, we know which bridges we have to assign higher priority for inspection and for repair. Okay, so everything is going to be based on these independent variables right here. That is fed into this list called features. Features becomes the X variable. These are all our independent variables, and we use the independent variable to predict the dependent. So this is dependent on this. Okay, so hopefully that makes sense. So we're going to use RandomForestRegressor in this case because all of these are numeric. Again, we either convert material to a numeric representation of itself using a couple different techniques, either one-hot encoding, categorical encoding, or label encoding, or we can just drop it from the data set completely. Okay, so there's 2 ways to handle that. But we do have to use regressor here to try to solve this problem and to make this prediction. Condition 5 years from now is good condition or bad condition. So when we run this, we can check our R squared. The R squared comes from right here. Okay, and the MAE is mean average error. So the R square is actually pretty high in this case. I'm very satisfied with this result. Closer to 1.0 is better. 0.99 is great. That means 99% of the time we are making accurate predictions. 1% of the time we could make a mistake, or the model makes a mistake, right? In this case, 96.6, almost 97% of the time we're making accurate predictions when we predict this target variable, when we predict what the outcome is going to be. 3% of the time the model makes a mistake. That's pretty de minimis. 3% of the time I'm not too worried about. 97% accuracy, that is pretty good right there. So, we're going to go ahead and set that as the target variable. We have the train and the test. So training, you can think of this as you are going to school. It can be grammar school, high school, college, working on your master's, PhD, doesn't matter. So the training is when you go to school, take your test, do your reading, study, do the homework, practice, things like that, right? The test is a test. So you train for several weeks. You take a midterm, train for a few more weeks, take a final, and that's your score, right? So depending on the outcome of the test determines how well you've learned the material. If you are getting 97% correct, then you've learned the material pretty well. That's an A, probably A plus in my book. And if it's lower, then you're not learning. But in this case, the model is learning quite well. So I'm pretty happy with that. So let me run this next cell over here. We'll see what the outcome is. So we have the training and the testing and 97% accuracy. So, 99.7 in this case. So this is area under the curve. So this is even better. So this is making a prediction on, let me see where this is. This is a classifier. So we're actually running 2 types of models right here. The RandomForestRegressor, which is giving us an R squared and MAE, mean average error. So pretty high in terms of its predictive capabilities. Here, this is a classifier. Remember, before we were using RandomForestRegressor, now we're using a classifier. So any kind of regressor is looking at numeric data. Anything that's a number, 1, 2, 3, 4, 5, or a float, this is totally fine, right? Anything that is not numeric is a classification type of problem. So anything that looks like concrete, steel, composite, anything non-numeric, it could be binary, it can be yes, no, true, false, on or off, things like this, or it could be a label. Concrete, steel, composite, it could be small, medium, large, extra large. If you're looking at sizes, if you're trying to predict the size of a garment, that would work as a classifier, right? So this looks pretty good over here, 99.7% accurate AUC, area under the curve. So that looks nice. And we are sorting in descending order by major defect 5 years now. So if you go over here to the right, major defect 5 years. And I see some ones over here, major defect in 5 years, zeros. So like I said, the classifier will give you true, false, yes, no, on or off, 1 or 0. 1 means yes, so there's a major defect over here. So these bridges right here need to be inspected right now, okay? So this is high priority. Anything that has a 1 is high priority. Major defect in 5 years, no, these are fine. These are totally fine. So the priority should be here. I'm just showing the top 5. You would want to go into, you see zeros over here, and the priority should be assigned to these bridges right here. There's another way to look at this too. We have risk score. If you look closely, the risk score came from back above. If I go to a control F, we can find risk score over here. This is actually an amalgamation of condition now, condition 5 years predicted value, major defect 5 years predicted, normal traffic, normal last inspection. Okay, and all of these have slight weights assigned to them. So it looks like 3 and 3 is 6, 7, 8, 9, and 10. So we get 100%. And these have a lesser weight, and these have a greater weight. Okay, so 30%, 30%, 20%, 10, 10. Okay, so hopefully that makes sense. So so now we are down to here, right? And let me see. Okay, major defect 5 years. So these bridges need to be inspected. These are being flagged as ones, so that's a major defect. These are fine, leave them alone. So if we want to look at the risk score, I just showed you how to create the composite risk scores from those weightings. So the risk score now, in this case, I am doing almost the same thing as before. Data frames sort values by major defect. Ascending equals false, so this means descending. So the highest is at the top. Same thing over here. Ascending equals false. There's really no descending. It's either ascending equals true, so it's going up in value, or ascending equals false, so it's going down in value. There's no descending, okay? So risk score, now we're looking at the risk score up here. Okay, and it should pretty much correspond to the major defect, although there could be some deviations because it's a different type of metric. So you can see 0.68, 0.67, 0.64. It's decreasing in order of most important to lesser and lesser importance. So that is the head over here. This is the tail, 0.08, 0.08 down to 0.05. So this is more like the risk is only 5% over here at the tail end of the 2000 records that we're looking at. This has a high risk, 68, almost 69% risk, though this is over 2/3 high risk, right? So 2/3 the probability or 2/3 weight that this bridge is in serious condition of disintegrating and decomposing and needs to be inspected and repaired, at least inspected and most likely repaired immediately, right? So this is top priority, number 2, number 3, number 4, number 5. So this is almost like a ranking order, okay? So hopefully that makes sense. Let me run the next cell here. So inspection year, here we're looking at 4 year and years, remaining year capacity per year. Inspection year equals the year. So we're taking everything and assigning that to inspection year. And DF sorted by inspection year. If we go over here, we should see that over here. So this looks like 3 years ago, this was inspected. These are NANs, not a number. So NAN is not a number. These are okay. This was inspected 3 years ago. So that's good to know. I'd be more concerned about these over here. So, oh, the risk score, right? 0.68 through 0.64. These are the top 5 most most likely at-risk structures right here. All these bridges. These have a much lower probability of some kind of catastrophic failure down here. Okay, so just different ways to skin the cat, different ways to look at it. But again, like I would focus on these, most likely major defect 5 years. These are the problem children right here. These are the problem childs or whatever children. And this is the risk score. So these are the top 5 most risky, and these are the least of 5 most risky. So overall, major defects, 0 is nothing. Don't have to worry about it. 34 have a major defect in 5 years. So 34 of the 2000 bridges need high priority. These need our full undivided attention right here. Okay, so we've taken this out from 2000 bridges that we could just randomly inspect and say, wow, this one kind of looks good, that one kind of looks good. It's not that. It's really based on science. It's based on math. It's based on statistics. This needs our attention right now. Okay, so I have some things in my notes right here. Probability the bridge will not have a major defect, 0, so we know those are fine. 1966 are fine. 34 are at risk. Anything that is at risk will be assigned to 1 major defect within the next 5 years, okay? And extremely high risk, inspect immediately if this is 0.9 or above. Medium risk, inspect next year. And low risk, this is expecting sometime within the next 3 years. Again, low priority, doesn't really require a lot of attention today. 0.9 immediate, 0.6 is pretty close. You're almost at 0.7. I would say if there's nothing in the pipeline, just go out and do it. Do the inspection. And most likely there is some kind of repair work or restoration needed for these top 5. These are down here are low risk. Sometime in the next, what was the rule here? Sometime in the next 3+ years, those can be looked at, right? So let me refresh this. We're getting close to the end, so hang in there, guys. So I'm looking at the major defect in 5 years. That is the X variable going on the horizontal axis and number of bins. So we're counting bins. This is going to be the Y axis. And this is my data frame right here. So I'm printing the data frame right here. Display data frame. This is what it looks like. Major defect within 5 years. Let me look over here. Major defect within 5 years. Oh, yeah, probability of major defect within 5 years. So we're counting these, and we have, let's see, 1571 within the next 5 years. Again, not immediate. The immediate need is right here, these 5. Look at the risk score. But within the next 5 years, actually, we have 1,571 bridges that need attention, right? So there's a lot of work to be done here, guys, a lot of work. A similar but different type of plot over here. So we have additional traffic on the x-axis. So again, x is horizontal, y is vertical. Probability of a major defect within 5 years. And we are plotting this right here. So major defect within 5 years. Anything that is a yellow is going to have a major defect, right? That's what we presume. You can zoom in. I love these charts because you can zoom in and zoom out, and you can see all the details here. And that is going to, let me see. That's fine. That's fine. Okay. Just looking at this, yeah, everything's fine here. So anything that is blue down here, major defect in 5 years, pretty low average daily traffic. The more traffic, probably the more risk. Less traffic, less risk, right? Just less stress, less use of the bridge. And anything in yellow is high risk. This actually is purple. It's sitting among the yellows, but this bridge seems to be in good shape right here. So that one doesn't need a whole lot of attention. These others really do need attention, right? Anything that's yellow should be high risk. I always say a picture is worth 1,000 words, right? So there's the graphic to illustrate which bridges need the immediate attention. And again, if you go back here, anything with a high risk score is going to be basically yellow down here, okay? So those two correspond pretty well. I can delete this. I'm not really using that thing right here. So that's gone. Let me save. Let me save my change here. Okay, so we have average risk by scheduled inspection year. So within the next 1 year, we have average risk score of 0.50, 0.426. Next 2 years, 0.378. And you can see the risk is decreasing as we increase the inspection year, because these bridges 3 years out is in pretty good condition for the most part. Somewhat of a risk, 0.37, not high, not going to lose any sleep about it. 2 years out, we have average score of 0.42. Risk, this is 0.50. So we're 50% of the chance, 50% of the way to risk, right? And we said before, like these high risk items over here, this is 5.6, 0.6 over here, 0.58. I was trying to look for this one. This is 0.58. This is 0.58. Anything over 0.5 is high risk, and we should draw our attention to that within the next year. 0.4 within 2 years, and 0.37 is within the next 3 years. Okay, so I think this is pretty much it. We can wrap it up. So again, x-axis is horizontal, y is vertical. So we're looking at risk scores here. We have concrete, material, and composite, and we see a box plot right here. So you can tell it's a box plot by this right here. That's the name of the plotly chart. So you see all of the in-between median Q3, Q1. So this is quartile 3, quartile 1, the lower and the upper. You see the max is 0.65, max risk is 0.65 for concrete, 0.69 for steel, and 0.64 for composite. This just shows you the distribution of all the risks, the median, the average, the min, the max. It's a good variation of the distribution of risks based on the type of material that the bridge is composed of. So that's it, guys. That is my take on bridge deterioration prediction and inspecting or scheduling inspections for said bridges. Okay, so I'm going to wrap it up right here. I just saved this. I'm going to download the file, save as HTML. Okay, and I'll share all this code with you guys. When I post the video, I'll do that later tonight. I'll throw it up on YouTube probably soon here. It's getting kind of late in the day. Today is December 2nd, 2025. Before I go to sleep tonight, I'll post a video and I'll post all the source code so you have everything you need. You can dig in and start your own analysis here and tell me what you think. leave some comments in the comment section, and go ahead and subscribe to the channel. Helps me a lot. Still trying to make some money and monetize this thing. I have about 460 videos. I've been doing this for not quite a year and a half, but almost a year and a half. Still made $0, still zero. But I'm not going to give up. I'm not going to throw in the towel. I'll keep going and keep at it. And hopefully someday I'll get over that hurdle, score a touchdown here, and start making some money. Even when I do, I'm sure it's going to be pennies. I'm sure it's not going to be anything big or life-changing. I'm giving up on that. All right. I'm just trying to just get over the 4,000 hours viewed and just get some kind of monetary remuneration. And if I get a couple pennies, I'll be happy. That's good to go. Okay, that's it, guys. I'm going to sign off here. Thanks for your time. Thanks for sticking through to the end. I'll post a video soon, just like I promised. I've got a couple more on the back burner. I'll throw those up in the next probably 24 to 48 hours as soon as I get a chance. Okay, so thanks again, and talk to you soon. That's it for this one. I'll see you in the next video. Bye.